For this lesson, we're going to be taking a look at what is probably the central theme to this entire course. And you could argue that it is an integral part of the next two courses, which is the idea of relations and functions. The title of the course itself is functions, so obviously that plays an important part. Relations are things that you should already be well familiar with as you've worked through your grade 9 and 10 math courses. You've got introductions to linear relations and quadratic relations, so you're familiar with that word in that context. A more formal definition of a relation we have here is a set of ordered pairs. That's just like saying a list of ordered pairs. So basically a list of points that relates your independent variable. If we don't have a good reason, we normally label our independent variable x and your dependent variable. And again, unless we have a good reason to label it something else, we typically call it y. Now that set of ordered pairs can actually be presented different ways. One way is the literal list or set of ordered pairs, which is a list of ordered pairs. These are the points in my relation. If I've got a list of points, another way that I could represent that would be as a graph. So I could take a known list and plot them on a graph, or you could be given a graph that just has some points pre-plotted for you. Then you might also have the situation, and this is actually the type of relation that you've dealt with the most up until this point, which is a relation that has a specific pattern, and you can represent that pattern using some sort of equation, an algebraic representation. So in this case here, I have the equation of a straight line. This equation, without any other information being given to us, we would interpret this as representing an infinite number of points. So it is still a set of points, but the set of points here is an infinite number of points. Obviously, there is no way that we could list them. Even for a large number of points, we wouldn't want to list them. And for an infinite number of points, it actually becomes impossible. But thankfully, we have this nice, concise algebraic notation to use instead. The idea of a relation can actually be quite a bit broader than what I've described there. It can encompass basically any two categories of data, and you can compare them in a relation. You might use qualitative data, so a description, or you might use quantitative data. Now in math, we are obviously much more preoccupied and focused on the idea of quantitative data, but just keep that in mind that you can actually make a relation a number of different ways. This blue background, I wouldn't include that in any class notes. I'm just putting it here for discussion. So you can see any one of these headings could be used as part of my relation. I could have the relation between the month and the total rainfall. I could have the relation between the daily maximum temperature and the mean number of rain days. Sometimes there's going to be some sort of correlation in those relationships. You might be able to make a mathematical model, which could be an equation, or you just might end up doing a scatter plot of the data if it's numerical. Now, I'm going to introduce this topic. I'm going to cover it in more detail in a lesson dedicated to this idea of domain and range, but I'm introducing it here just so you start to gain some familiarity with it. Again, this is a theme that's going to run its way through this entire course and into the next course. Domain is the set of all possible values. You notice we're emphasizing this word set again and again. So the set of all possible values for the independent variable, which we typically call x. Range, the set of all possible values for the dependent variable, that's typically y. So you see here I have a list of points, and then I ask to state the domain and range. And I say to state it because you don't have to figure anything out here. You just look at it, you do it by inspection. So in this case, my domain is equal to, now my domain is going to be a set of numbers or a list of numbers. Here I had a set of points. The domain is made up of the x coordinates from those points. And typically, so long as it's not too much of a burden for you to do so, you typically want to write these in numerical order if it's reasonable to do so. And it's important that you do not include any duplicates. So let's take a look at our x values here. The lowest x value is -3, and then I see a -1, and then a, what else do we have? A 1, a 2, and a 4. And that would be the domain in set notation. The range is doing the exact same thing, but in this case with the dependent variable, which would normally be called the y-coordinate. And so once again, since there's only 5 points here, the lowest value I have is -1. The next value I have looks like a 3. In that case, notice that the 3 is a duplicate value. It appears twice. There's nothing wrong with that. This range is still valid. It just means that I only write the number 3 once. And I also have a duplicate in the 5. And so this range is 1, 3, and 5. The domain tells you all the x values that occurred in your list of points. The range tells you all the y values. This is just, I've just repeated the definition here. So the note continues here in the black text. And here's another way I can take those set of points before I get to domain and range. I can also have this other method of representing a relation. And this is known as a mapping diagram. It basically tells you all the values in the domain. So you can see in this bubble on the left, which represents the domain, that lines up with the actual set notation of the domain. And in this bubble on the right, I have the range, and that lines up or corresponds to the range I've listed over here to the right. And then what a mapping diagram does is it actually tells you how do values in the domain map onto the range. So if I'm reading this, I see this 0 maps onto 1. That tells me that there is a point 0, 1. And then I take a look at this 2, it maps onto a -5 and onto a -10. And so that tells me about 2 different points because each of those arrows represents one of the points in your relation. And then finally 3 maps onto 4, which is represented there as a point. We don't make a lot of use of mapping diagrams. I've included this for completeness. Our textbook, the exercises that I've assigned out of our current textbook, they make reference to it. So I included it here just so you weren't sitting there scratching your head and wondering what that meant. Now we get to the word that figures so prominently in the title of the course, function. The next course after this is known as advanced functions. So a function is a subset of relation. It's a special kind of relation where each value of the independent variable is only going to give a single value of the dependent variable. And we'll talk in a moment about the implications of that. But first, I'm just going to give you a set of rules to help you remember and identify whether or not you have a function, because a lot of times that's what you're going to be looking for. In set notation, none of your x values are repeated. So if we think back to this example we did, notice that there were 5 points and I ended up with 5 values in the domain. None of those x values were repeated, so this set of points actually represents a function. You can also have a graph. So if you have those points or if you have a line that's graphed, you can perform something known as the vertical line test. And so long as a vertical line never goes through more than 1 point, then you have a function. If it goes through more than 1 point, you have failed the vertical line test and it is not a function. And then in the case of an equation, the best way, unless you recognize what kind of relation the equation represents, the best way that you can determine using an equation is to rearrange it for y. And then I say to ensure there is only a single value. And just saying that in words is actually confusing. I hope that's going to make more sense when I illustrate that with an example, which I'm going to do down here in part B. Now I've given myself a little bit of room to work through these, so let me go ahead and just jump to those. So determine which relations are functions out of these examples. Here I have a set, and I don't need to write this out, but I'm going to do so. The domain of this one is, and I take a look at my values, I start with the lowest value, 1, 3, 4, 7. And there were no repeated values in the domain. So no repeats in the domain, therefore it is a function. Let's take a look at the algebraic one. Not nearly as simple, certainly not something you're necessarily going to see by looking at it. It said to rearrange it for y. So the first thing, let's isolate the variable y squared, and that's going to become 25 minus x squared. Now I've got y squared, so I have to get y all by itself, and the operation that gets rid of a squared is a square root. So we end up with 25 minus x squared under the square root. But this is a super critical part. You actually need to say plus or minus. Now the reason for that, imagine I said y squared was equal to 9. What value can you square and get 9? And the answer to that is I could square 3, but I could also square -3. And this should be an argument that you've seen many times. So that means that y is actually equal to, when I use the square root to isolate the variable by getting rid of that squared, y is actually equal to plus or minus the square root of 9. That's why we have to introduce that plus or minus. Now in this case, y equals positive square root or negative square root. That actually means that this y has two solutions. One of them is the positive square root, 25 minus x squared, and one of them is the negative square root. Y equals negative the square root of 25 minus x squared. For any value of x that I put in here, I potentially could get two different values of y. And that violates the idea of a function. A function needs to be predictable. When you put in a particular value for x, it can only generate reliably a single value for y. In this case, because we could potentially generate two values for y, it's not a function. Now again, just another little aside here to help illustrate that idea. Here's an example of a function. This is what's known as a substitution cipher. So this is the most basic form of encryption. This was used hundreds or even thousands of years ago as the most basic way to construct secret messages. And you can see this one just uses a shift in the alphabet. So in this case, all of the letters have been shifted over by 3. So A lines up with D, B lines up with E, C lines up with F. For this to really work successfully, you need this to be a function, and think about why that's the case. It's that idea that for any input, you need to have a predictable output. It wouldn't be useful if the letter F sometimes matched up with the letter D and other times matched up with the letter I. That would be a terrible cipher because you wouldn't actually be able to generate a reliable message. So the idea of a function is that an input generates a reliable or consistent output. Now we're going to revisit that equation, that relation that we said was not a function. Sorry, I should actually finish this off just with a final therefore. Therefore, it is not a function. And I'm going to revisit this particular equation, x squared plus y squared equals 25. That should be familiar to you, depending on what you covered in your grade 10 course. So we're going to come back to that. You might want to give some thought to what does that relation actually represent? It's a named relation, and you should be able to figure out what the graph of that looks like. For now, let's start with something easier, y equals x squared. And I'm just asking to sketch. More and more often, as you do more advanced levels of math, we leave the graphing quite often, precise graphing, for software. But we do a lot of sketching because it can provide a lot of information and it's a very powerful technique. In the case of y equals x squared, that is a parabola with a vertex at the origin. It opens up, and so it looks roughly like that. Then I'm going to perform what's known as the vertical line test. If you're doing this in your notes, you can just visualize it, or you can lay down a ruler and then grab that ruler and slide it along your graph. And so long as the ruler only ever touches one point at a time, that is a pass of the vertical line test. In this case, you can see the parabola does pass the vertical line test. And so I'm just going to put that here, that it passes. We normally call the vertical line test the VLT. That's a perfectly acceptable contraction, a short form for the vertical line test. So therefore, it is a function. And that is true for any parabola. All parabolas are functions, because no matter what parabola you draw, whether it opens up or down, it's going to pass this vertical line test. Now, you've had a little bit of time to think about x squared plus y squared equals 25. If you haven't thought of it by now, that is the equation of a circle. And specifically, the general equation of a circle is x squared plus y squared equals r squared. So this is actually a circle with radius 5. Now, I'm not going to try my hand at drawing a circle. I'm going to use the tool that I have available. So I'll just draw in a circle very nicely that way. I will label the fact that the radius of this circle is 5 units. And then we think about, okay, well, what we're really interested in is whether or not this is a function. And so once again, I've already got my vertical line, so why don't I just go over here and grab that vertical line. It's currently crossing 0 points, and that happens with functions sometimes. So that the fact that it's not crossing anything, that doesn't mean it is or is not a function. That just means so far it might be a function. Then I get to this very edge, and that's what's known as a tangential line. A tangential line is only crossing that graph one time, so it still could be a function. And then the moment I inch a little bit further to the right, I'm now crossing the function, or sorry, I'm now crossing the relation at 2 separate points, 2 points, 2 points, and that carries on until I get to this other tangential line or tangential contact, and then I drop down to 0 again. So obviously, this one fails the vertical line test because there were many times when it was touching the graph twice. So this one fails the vertical line test, and therefore it is not a function. And just another comment about graphs. Again, I wouldn't include this in my notes, but I do want to comment on it. Because we're going to be also talking about sets of points and graphing, it's worth it to just make this distinction, just to put it there in your mind. We're still primarily going to be dealing with relations and functions that can be represented using an equation. And those are most of the time going to represent a continuous relation, so an infinite number of points. But we will plot them using distinct points. On the other hand, if you get a list of points, they may lie along the exact same line. You might look at that and say, oh, that's a straight line, and particularly from your grade 9 course, but I would also say in grade 10, your habit is just to draw points and then to draw a curve or a line through those points. And I just want you to remember that's not always going to be appropriate. If you are just plotting a list of points, that's the end of it. Those points plotted, that is the entire relation. So just something that you do need to keep in mind going forward. And then that's it to wrap things up. Here's some assigned work from our current textbook to help you practice these skills.